Alright, so in a previous screencast called Real Zeros, we learned how to find real zeros of polynomials. It turns out that polynomials also have complex zeros. In other words, they have zeros that involve imaginary numbers. And to get things going, we're going to talk about the fundamental theorem of algebra. And what it says is for every polynomial p of x of degree n greater than 0, it's going to have at least one zero in the complex number system. So that means if we've got a polynomial, we're guaranteed to have at least one zero of that polynomial in the complex number system. Okay, now by itself that's not so useful, but a corollary of this theorem is called the n zeros theorem, and it says that for every polynomial of degree n greater than 0, blah blah blah, it says it can be expressed as the product of n linear factors. So in other words, the number of factors matches the degree. In other words, p of x has exactly n zeros. Now, it may be the same zero counting once or twice or 3 times, depending on the multiplicity of the factor. But if you have a 3rd degree polynomial, you're going to have 3 factors. If you have a 10th degree polynomial, you're going to have 10 factors. And our third and final theorem for this screencast is the complex conjugate zeros theorem. And it says that if a polynomial has real coefficients, so folks, it's got to have real coefficients, not complex coefficients. And if a plus bi is a zero of p of x, then its complex conjugate, a minus bi, is also a zero. In other words, if you have one root or solution or zero that is a plus bi, you are guaranteed to have a partner a minus bi. Complex solutions always come in conjugate pairs. So here's an example. Find all zeros, real and complex, of this polynomial x to the 4th minus 25. So I'm going to set it equal to 0. And I notice that it's the difference of 2 squares. So I'm going to factor that. X squared minus 5, x squared plus 5. And this is, both of these are also the difference of 2 squares. Well, you may be saying that's not the difference of 2 squares. Well, actually it is. What if I wrote it like this? X squared minus 5, x squared minus negative 5. Okay, so this is going to factor into x minus the square root of 5, x plus the square root of 5, and this will factor into x minus the square root of negative 5, which is I root 5, times x plus the square root of negative 5, which is I root 5. So our zeros are plus or minus root 5, those are the real ones, and plus or minus I root 5, those are the complex ones. Okay, how about if I know I have a polynomial of degree 3 and I know 2 of the zeros? One of the zeros is 1 and the other 0 is negative 1. Well, that is a complex number. It's imaginary, so we know that there is also going to be another root, which is its conjugate, positive I. So here we go. P of x is x minus 1, that takes care of that 0, times x plus I, that takes care of that 0, times x minus I, and that takes care of that 0. Okay, so let's do FOIL. That'll give me x squared minus 2ix, nope, sorry, what am I thinking here? Minus 1ix plus 1ix minus I squared. I squared is negative 1. So this is x squared minus negative 1, which is x squared plus 1. And then finally I can multiply that out, and I'm going to get x cubed minus x squared plus x minus 1. And that is a polynomial that has zeros 1, negative I, and positive I, and it's degree 3. Okay, now let's say we're given that we know 1 plus I is a 0 of this polynomial. Let's get all the other zeros. So there's 3 others we have to find. Okay. All right, I'm going to take a little side trip here and tell y'all a little trick here. If I have 2 zeros, R1 and R2, then the quadratic that contains those zeros is going to be x squared minus the sum times x plus the product. Okay, so I'm going to make a quadratic with 1 plus I is our first root and 1 minus I is our second root. Okay, so the quadratic containing these two zeros, and I know that both these are zeros of this polynomial because remember they come in conjugate pairs. So I'm going to have x squared minus the sum of these. Okay, the i's cancel and I get 2 plus the product. Okay, that's going to be 1 plus I, 1 minus I. That's going to be 1 squared minus I squared, which is 1 minus negative 1, which is 2. Okay, so this quadratic is a factor of this polynomial. I'm going to divide it, and my quotient will give me my final two zeros. I need to put a 0x cubed minus 9x squared plus 18x minus 14. If we don't get a remainder of 0, we know we've done something wrong. So I'm going to go x squared. It's going to be x to the fourth. X squared times negative 2x is minus 2x cubed. X squared times 2 is plus 2x squared. Subtract. I'm going to get a positive 2x cubed and then a negative 11x squared. Bring down the 18x. I'm going to do a plus 2x. 2x cubed minus 4x squared plus 4x. Subtract. And I'm going to get negative 11 plus 4 is negative 7x squared plus 14x minus 14. Put a negative 7 there. Negative 7x squared. Negative 7 times negative 2 is plus 14x. It's looking good. Negative 7 times 2 is negative 14. Yes, we get a remainder of 0. Okay, so this times this will give us our original polynomial. Okay, so the roots of this piece are 1 plus I and 1 minus I. What are the roots of this quadratic? Well, let's just use the quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And that'll be negative 2 plus or minus the square root of 4 plus 28, which is 32 over 2. I can take a 16 out of that, so it's going to be negative 2 plus or minus 4 root 2 over 2, which is, I'm getting sloppy, aren't I? Which is negative 1 plus or minus 2 root 2. All right, so what are our roots here? We have 2 real roots, and we have 2 complex conjugate roots for a total of 4 zeros. Last example. So let's factor this polynomial. What do we know? Well, all we can do is use our rational zero theorem, which says that any possible rational zeros are going to be all the factors of this constant divided by all the factors of the lead coefficient. So possible rational zeros are going to be plus or minus 1 and plus or minus 3. Okay, so let's try 3. One x to the fourth minus 2x cubed minus 2x squared minus 2x minus 3. 3 times 1 is 3, minus 2 is 1, times 3 is 3, minus 2 is 1, times 3 is 3, minus 2 is 1, times 3 is 3, 0. Okay, and let's try negative 1. Negative 1 times 1 is negative 1, 0, 0, 1, negative 1, 0. Okay, how do I know those are going to work? Because I worked them out ahead of time. So what do we know right now? We know that these two are real roots, so x equals positive 3 and negative 1, and this tells us that x squared plus 1 has to equal 0. That means x squared has to equal negative 1, which means that x has to equal plus or minus I. So those are our two complex conjugate roots. And if we want to write it as a factor, then I'm going to say p, let's do this farther on down, okay? P of x is equal to x minus 3 times x plus 1 times x minus I times x plus I. And that's our original polynomial written as a product of linear factors.